All right, welcome. Today, we're going to tackle something that's literally everywhere, but most of us never see it, the programming language. I mean, think about it. From the operating system on your phone to the games you're obsessed with, these languages are the invisible blueprints of our digital world. But how do they actually work?
Yeah, it's a huge question, right? How does some creative spark in a developer's mind end up as the app you're scrolling through right now? Honestly, it can feel like pure magic, but it's not. It's really a process of translation. And right at the heart of it all is a very, very special kind of language, one built specifically to talk to machines. So, yeah, that's the key word translation. We've got to take our human ideas, our intentions, and somehow turn them into a form a computer can understand and execute. We need a language of pure logic, and that's exactly what programming languages are. They're the bridge that lets us cross from human creativity into the world of machine logic.
Okay, so let's get right into it. What exactly is a programming language? And what are the rules of the road for this whole translation game?
Well, at its most basic level, it's a language that humans made up. It's artificial. And here's the crucial difference. Unlike English, which can be super vague and ambiguous, where one sentence can mean three different things, a programming language has to be perfectly precise. Its entire job is to give a computer a list of instructions that it can follow to the letter, with zero confusion.
And just like any language you or I speak, they've got two main parts. You've got syntax, which is basically the grammar, the rules for how you arrange all the words and symbols. And then you have semantics, which is the meaning. You can think of it like this. Syntax is getting the spelling and punctuation right. Semantics is making sure the sentence you just wrote actually means something sensible. And this is maybe the perfect example to drive that point home. This famous sentence from the linguist Noam Chomsky. It's grammatically flawless, right? The syntax is absolutely perfect. But it's complete gibberish. It doesn't mean anything. It has no semantic value. And this happens in programming all the time. You can write code that follows all the grammatical rules perfectly, but what you've told the computer to do is just nonsense. And that's how you get bugs or just really, really weird program behavior. So where did all this even come from? Well, the very first programming languages were a huge leap forward. I mean, a revolutionary idea. It was a total shift from forcing humans to think like a machine to finally teaching the machine to understand, well, something a little more human. You have to picture this. Back in the 40s, there were no languages like we think of them today. Programming meant physically feeding the computer raw machine code, literally just ones and zeros. It was an absolute nightmare. It was tedious, and finding a single mistake, one misplaced digit, could take days. And the worst part? The code you spent all that time on would only work on that one specific machine. It was a dead end. So clearly something had to change. And the solution was to build what you can think of as a ladder of abstraction. We were climbing away from the machine. At the very bottom, you have that raw machine language, the ones and zeros. The first step up was assembly language, which was a little better. It used short codes, mnemonics, instead of just numbers. But the real game changer, the revolution, was that third step, high-level languages. Suddenly, we were using words and math symbols that actual humans could read and understand. And this breakthrough just opened the floodgates. It was a creative explosion. In '57, you get Fortran, which was a massive deal for scientists and engineers. Then, just a year later, Lisp comes along, introducing these mind-bending concepts like treating code as data, an idea that's still a huge deal in AI research. And then, by 1960, ALGOL arrives and basically sets the standard, becoming the granddaddy of so many of the languages we still use. So with these early successes, the gates were wide open. And as people started using computers for all sorts of different problems, it became super obvious that a one-size-fits-all language just wasn't going to cut it. You needed different tools for different jobs. And on top of that, different programmers had totally different ideas, different philosophies about the best way to solve problems. And that's where we get this idea of programming paradigms. It's a fancy word, but just think of them as different schools of thought or entire philosophies for how to build software. It's kind of like the difference between writing a step-by-step recipe versus drawing a detailed blueprint versus just snapping together pre-built parts. They're all valid ways to build something, just different strategies. So let's break down the big ones. Imperative programming is the recipe, a simple step-by-step list of commands. Do this, then do that. Functional is more like a math problem. It's all about taking some data, applying functions to it, and getting a result. Object-oriented. That's like building with Legos.
You create these little self-contained objects that have their own stuff inside them and know how to do certain things. And then there's logic programming, which is pretty wild. It's like telling your GPS, I want to go to the grocery store, and just letting it figure out the best route. You describe the goal, not the steps.
Okay, so that's the ancient history. How did we get from those foundational ideas to the languages that are running basically everything today? Well, the answer is a massive shift, a real earthquake, caused by two things we all know very well, the PC and the internet. First, the personal computer put a computer in every home, creating this huge market for software. But it was the internet that really, truly changed the game. All of a sudden, the rules were completely different. Your code had to run on any machine, anywhere in the world. It had to be secure from hackers, and you had to build it fast. And on top of all that, our computers were getting way more powerful, with multiple processors, multiple brains in one box, and languages had to evolve to take advantage of all that new horsepower.
Yeah, the problems we were trying to solve just fundamentally changed. Suddenly, being portable, the ability to run your code anywhere, wasn't a nice to have. It was absolutely critical. Security went from being an afterthought to priority number one. And because the web moves at the speed of light, you needed languages that let you build things fast.
And this new reality gave rise to the titans of the web era. You had Java with its famous promise, write once, run anywhere. I mean, that was perfect for the internet. And then you had this explosion of what we call scripting languages: Python, JavaScript, PHP, Ruby. Their whole reason for being was speed of development. They let programmers whip up dynamic, interactive websites way, way faster than the old tools. Which brings us right up to today. So after all that history, all that evolution, after hundreds and hundreds of languages have been created, which ones actually won? What are the tools that developers are reaching for right now to build our world? Well, if you look at a popular ranking like the TOB index, the top three are Python, C++, and C. And that's a really interesting mix because it tells a story. Python is king right now, mostly because it absolutely dominates in the exploding fields of AI and data science. But look at C and C++. These are direct descendants of some of those really early languages. They've stuck around because they're blazingly fast and super efficient. For anything where performance is everything, like your computer's operating system or a complex video game, they are still the top choice. And that really is the big takeaway here. The entire history of programming languages has been about building a bigger and more specialized toolbox. We don't have just one hammer anymore. We have a whole workshop. And the toolbox got bigger because the jobs got more varied. So today, a developer picks Python for an AI project, JavaScript for a website, C++ for a new game engine. It is all about picking the absolute best tool for that specific job.
Which leaves us with one last and pretty mind-blowing question. The whole story we've just talked about has been about humans building better tools to talk to machines. But now we have AI, which is a tool that is starting to write code and even build other tools on its own. So what happens next? What's the next big idea, the next great leap in this incredible journey of translating human thought into digital reality?